the discovery that changed everything. On a cold February morning in 2025, Dr. Elena Reeves stood frozen in front of her monitor at the Space Telescope Science Institute in Baltimore. The data streaming in from the James Webb Space Telescope showed something that shouldn't exist, not according to any model, any theory, or any prediction made by cosmologists over the past century. The galaxy cluster she was observing, designated JWST 2025 Alpha, existed at a distance that suggested it formed merely 300 million years after Big Bang. But that wasn't the shocking part. The shocking part was its size. "This can't be right," she muttered, running the calculations for the third time. The cluster contained a mass equivalent of 1 trillion suns, spread across a region of space that dwarfed anything found in the early universe. According to everything humanity understood about cosmic evolution, such a structure simply couldn't have formed that quickly. The universe at that age should have been a cosmic infant, still assembling its first stars. Yet here was evidence of a fully mature galactic metropolis, thriving in an era when the cosmos was supposed to be primitive. Dr. Reeves picked up her phone and dialed her colleague at the European Space Agency. "Marco, you need to look at the JWST data from last night's observation run. Section 47B. Tell me I'm not losing my mind." 3,000 miles away in Madrid, Dr. Marco Castellano pulled up the files. His silence lasted almost a full minute before he responded. "Elena, this is impossible. These structures, they're everywhere. How many observations have shown this pattern?" 17 confirmed so far, Elena replied, her voice shaking slightly. "And that's just from our survey field. If this is representative of the entire early universe, then we need to completely rewrite our understanding of cosmic history." The James Webb Space Telescope, launched in December 2021, had been designed to peer deeper into space and time than any previous observatory. Its massive 6.5-meter mirror, protected by a tennis court-sized sunshield, collected infrared light from the most distant corners of the universe. Where the Hubble Space Telescope could see galaxies as they appeared a billion years after the Big Bang, JWST pushed that boundary back to just a few hundred million years, capturing light that had traveled for over 13 billion years to reach Earth. But no one had anticipated what it would find. Within weeks of the initial discovery, astronomical teams across the globe began reporting similar findings. The Max Planck Institute for Astronomy in Germany detected massive elliptical galaxies at redshifts of Z equals 10 and beyond, corresponding to times when the universe was less than 500 million years old. The Tokyo Observatory confirmed the presence of supermassive black holes with billions of solar masses in these ancient galaxies. The Australian National University's team found evidence of heavy element enrichment in stellar spectra from this era, suggesting multiple generations of stars had already lived and died. Each discovery added another crack to the foundation of the standard cosmological model. Dr. Rebecca Thornton, a theoretical astrophysicist at Cambridge University, explained the magnitude of the problem during an emergency conference call with leading cosmologists. The lambda CDM model predicts a hierarchical formation of structure in the universe. Small fluctuations in the cosmic microwave background grow over time through gravitational collapse. First you get stars, then small galaxies, then those merge to form larger galaxies and clusters. This process takes billions of years. What JWST is showing us is the equivalent of finding a fully constructed skyscraper before the cement factory has even opened. The crisis deepened when teams began analyzing the spectroscopic data in detail. The galaxies weren't just surprisingly large, they were surprisingly mature. Their stellar populations showed evidence of being hundreds of millions of years old, which would push their formation back even further, possibly to within 100 million years of the Big Bang itself. Some contained red giant stars, which form only after billions of years of stellar evolution. The implications were staggering. Either the universe was older than 13.8 billion years, or the laws of physics operated differently in the early cosmos. As news of the discoveries began leaking to the scientific community, research teams worldwide scrambled to access JWST observing time. The Space Telescope Science Institute received over 4,000 proposals for emergency observations, a tenfold increase from a typical cycle. Everyone wanted to confirm the findings, to find a flaw in the data, to somehow restore order to a universe that suddenly seemed alien and incomprehensible. Dr. Jonathan Way of the California Institute of Technology proposed an alternative explanation. What if we're misinterpreting the redshift data? Perhaps there's an unknown source of cosmological dimming that makes these galaxies appear more distant than they actually are. Some kind of exotic dust or an unexpected interaction with dark energy could be skewing our measurements. His team spent 3 months testing this hypothesis, analyzing every possible source of systematic error. They examined gravitational lensing effects, checked for calibration issues in JWST's instruments, and modeled dozens of alternative scenarios. In the end, they published a paper confirming the original findings. The galaxies were exactly where they appeared to be, exactly as massive as the initial measurements suggested, and exactly as impossible as everyone feared. Meanwhile, Dr. Amelia Zhao at the Harvard-Smithsonian Center for Astrophysics pursued a different angle. She focused on the cosmic microwave background, the afterglow of the Big Bang itself. The Planck satellite had mapped this radiation with exquisite precision, revealing the tiny fluctuations that seeded all cosmic structure. Dr. Zhao's team reanalyzed the Planck data, searching for any anomalies that might explain how such large structures could form so quickly. What they found was both enlightening and disturbing. In certain regions of the CMB, the fluctuations were indeed larger than expected, but only by about 20%. That difference, while statistically significant, couldn't account for the galaxy clusters JWST was observing. Something else had amplified those initial seeds of structure, something that current physics couldn't explain. We're missing a fundamental piece of the puzzle. Dr. Zhao announced at the American Astronomical Society meeting in June 2025. The universe isn't just bigger than we thought, it's stranger. There's a mechanism for rapid structure formation that we've never encountered before. It could be related to dark matter behaving differently in the early universe, or perhaps there's an entirely new form of matter we haven't discovered yet. The crisis in cosmology sparked a renaissance in theoretical physics. Young researchers, unburdened by decades of investment in existing models, began proposing radical alternatives. Some suggested modifications to Einstein's theory of general relativity that would allow gravity to operate more efficiently in the early universe. Others invoked primordial black holes as seeds for rapid galaxy formation, or proposed that the universe underwent a secondary period of inflation that amplified structure in specific regions. Dr. Yuki Tanaka, a graduate student at Kyoto University, made headlines with a particularly audacious proposal. She suggested that the universe might be far older than 13.8 billion years, with the Big Bang representing not the beginning of everything, but rather a phased transition from a previous cosmic state. In her model, structures could have begun forming before the bang itself, carried to the transition like ice crystals surviving a phase change in water. Think of it like boiling water, she explained in a viral interview. When water boils, it doesn't destroy all structure. Bubbles form, currents persist. What if the Big Bang was similar? What if there was a before that seeded the after with pre-existing structure? Her paper received both acclaim and harsh criticism. Established cosmologists argued that such a model contradicted observations of the cosmic microwave background and the abundance of light elements formed in the first minutes after the bang. But younger researchers found the idea compelling, and several groups began developing mathematical frameworks to test whether a pre-bang universe could leave observable signatures. Dr. Marcus Beaumont at Oxford University took a different approach entirely. He revisited theories of modified gravity that had fallen out of favor in recent decades. Working with a team of mathematical physicists, he developed a model where gravity's strength increased logarithmically with distance during the first few 100 million years of cosmic history. Under such conditions, massive structures could collapse and form on timescales 10 times faster than standard physics would allow. The beauty of this approach, Beaumont explained, is that it makes testable predictions. If gravity operated differently in the early universe, we should see specific patterns in how galaxy clusters are distributed spatially. JWST can test this directly by conducting deep surveys of multiple independent regions of the sky. The Space Telescope Science Institute immediately approved 3 major programs to do exactly that. Over the next year, JWST would observe 10 deep fields, each covering an area equivalent to a grain of sand held at arm's length, but looking back through cosmic time to the earliest epochs of structure formation. The data would either confirm or refute the modified gravity hypothesis, and potentially reshape humanity's understanding of the universe itself. As 2025 progressed, the astronomical community found itself divided into competing camps. Conservative researchers maintained that the standard model could accommodate the new observations with minor adjustments. Perhaps the efficiency of star formation was higher in the early universe, or maybe dark matter clumped more efficiently than simulation suggested. With enough tweaking, they argued, the existing framework could survive intact. But a growing contingent of scientists rejected this approach as intellectual cowardice. Dr. Sarah Kim, a respected cosmologist at MIT, delivered a scathing critique at the International Astronomical Union Symposium in August. We're not talking about small discrepancies that can be patched over. We're talking about observations that directly contradict the fundamental timeline of cosmic evolution. Continuing to cling to models that clearly don't work isn't science. It's dogma. We need to admit that something profound is wrong with our understanding and start from scratch. Her comments ignited a firestorm of debate. Editorials appeared in Nature and Science arguing both sides. Social media erupted with discussions about scientific paradigm shifts and the sociology of scientific revolutions. The controversy even spilled into mainstream news, with journalists comparing the situation to other moments in history when established scientific theories crumbled. The overthrow of geocentric astronomy, the quantum revolution of the early 20th century, the plate tectonics revolution in geology. Meanwhile, observational astronomers continued gathering data. Ground-based telescopes like the extremely large telescope in Chile and the 30-meter telescope in Hawaii pushed their capabilities to the limit, following up on JWST discoveries with complementary observations. The Atacama Large Millimeter Array measured carbon monoxide emission from distant galaxies, tracing their molecular gas content and star formation rates. Every new measurement added texture and detail to an increasingly complex picture. One particularly striking discovery came from the Chandra X-ray Observatory, which detected intense X-ray emission from several of the ancient galaxy clusters. The emission pattern suggested the presence of superheated intergalactic gas with temperatures exceeding 50 million degrees Celsius. Such gas could only be heated by violent processes, supernova explosions, black hole jets, galaxy collisions, all of which required time to develop. Yet here was evidence of extreme cosmic violence occurring when the universe was supposedly still peaceful and serene. By September 2025, the weight of evidence had become impossible to ignore. A consortium of 150 researchers from 45 institutions published a comprehensive analysis in the Astrophysical Journal, summarizing 18 months of JWST observations. The paper, spanning 97 pages and including over 400 figures, presented an exhaustive catalog of early universe structures that defied conventional explanation. The key findings were stark. More than 1,200 massive galaxies have been identified at redshifts greater than Z equals 10, corresponding to ages less than 500 million years after Big Bang. Their combined stellar mass exceeded predictions by a factor of 10 to 100. Spectroscopic analysis revealed that many contain multiple stellar populations with different ages, indicating complex formation histories spanning hundreds of millions of years. Some showed evidence of chemical enrichment from type Ia supernovae, which require billions of years to occur in standard stellar evolution. Galaxy clustering statistics showed that structures were far more evolved than cosmological simulations predicted. Instead of loose associations of small protogalaxies, JWST observed tightly bound clusters with hierarchical organization resembling modern cosmic structures. Supermassive black holes with masses between 1 and 10 billion solar masses have been detected in at least 40 galaxies from this era. The growth timescales required to form such massive objects exceeded the age of the universe at those redshifts by factors of 2 to 5. The paper concluded with a sobering assessment. The observations presented here are incompatible with the standard lambda-CDM cosmological model under any reasonable assumptions about astrophysical processes. Either the universe is significantly older than current estimates suggest, the laws of physics operated fundamentally differently in the early cosmos, or our understanding of cosmic evolution requires wholesale revision. The revelations from JWST forced the astronomical community to confront an uncomfortable truth. The universe was not only bigger than humanity had imagined, but bigger in ways that challenged the very foundations of physical understanding. The cosmos revealed by the telescope wasn't just unexpectedly large or surprisingly ancient. It was profoundly different from anything theoretical models had predicted. Dr. Elena Reeves, whose initial discovery had sparked a revolution, reflected on the implications during a documentary interview. We built JWST to answer specific questions about the early universe. What we didn't anticipate was that it would reveal how limited our questions were. We asked how the first galaxies formed, and the telescope showed us that our concept of first was naive. We asked how structures evolved, and it showed us that evolution wasn't the linear process we'd assumed. Every answer has generated 10 new questions, each more profound than the last. The philosophical implications resonated far beyond astronomy. If the universe was larger, older, or more complex than current theory suggested, what did that mean for humanity's place within it? The Copernican revolution had displaced Earth from the center of the cosmos. The expansion of the universe had revealed that even our galaxy was just one of hundreds of billions. Now, JWST suggested that the observable universe itself, everything within 13.8 billion light years, might be just a small fraction of a vastly larger cosmic structure. Some researchers began speculating about implications for the multiverse. If conditions in the early universe allowed for such rapid structure formation, perhaps the same physics operated in other cosmic regions beyond our observable horizon. Maybe the universe contained countless domains, each with slightly different properties, and humanity happened to inhabit one where the conditions allowed for particularly efficient galaxy formation. Others focused on more immediate concerns. Dr. Marcus Beaumont's modified gravity theory made specific predictions that could be tested within the next few years. If confirmed, it would represent the first major revision to Einstein's general relativity since its formulation over a century ago. The implications for physics would be revolutionary, not just for cosmology, but for our understanding of gravity at all scales, from subatomic to cosmic. As 2025 drew to a close, the James Webb Space Telescope continued its tireless observation of the distant universe. New scheduling priorities emphasized deep field surveys and follow-up spectroscopy of the most enigmatic early galaxies. Ground-based observatories coordinated their efforts to provide complementary data across the electromagnetic spectrum. Radio telescopes searched for carbon emission lines that could reveal the molecular gas content of primordial galaxies. X-ray observatories mapped the hot intergalactic medium surrounding ancient clusters. The European Space Agency announced plans to accelerate development of the Athena X-ray Observatory, originally scheduled for launch in 2035. The discoveries from JWST have completely reordered our priorities, explained ESA's Director of Science. We need X-ray observations with unprecedented sensitivity to understand the role of black holes and superheated gas in early structure formation. Athena can provide that, but only if we expedite the timeline. NASA responded by greenlighting preliminary studies for a successor to JWST, provisionally named the Habitable World Observatory, that would combine even larger aperture with advanced spectrographic capabilities. JWST has shown us that the early universe is far richer and more complex than we imagined, said the NASA administrator. But it's also revealed the limitations of current technology. To truly understand what we're seeing, we need the next generation of space telescopes with capabilities that push beyond anything currently available. Private space companies entered the fray as well. SpaceX announced a partnership with the Kavli Foundation to launch a constellation of small space telescopes dedicated to studying cosmic dawn. Blue Origin committed funding to develop advanced adaptive optic systems for ground-based observatories. Even cryptocurrency billionaires, seeking legitimate scientific endeavors to support, pledged hundreds of millions toward next-generation astronomical instrumentation. The influx of resources transformed the field. Postdoctoral positions in observational cosmology tripled. Graduate programs in astrophysics saw application rates surge by 400%. Young researchers, energized by the prospect of participating in a genuine scientific revolution, flocked to the field. The sense of excitement was palpable. This was astronomy's moment, a rare period in scientific history when fundamental assumptions were being questioned and revolutionary new ideas could flourish. Throughout early 2026, competing theoretical frameworks battled for supremacy in academic journals and conference presentations. Modified gravity theories clashed with models invoking exotic dark matter candidates. Proposals for primordial black hole formation competed with scenarios involving cosmic strings or domain walls from the earliest moments after the Big Bang. Each framework had proponents and detractors. Each made testable predictions, and each awaited confrontation with observations. Dr. Yuki Tanaka's pre-bang cosmology gained unexpected support from an unlikely quarter: quantum gravity researchers. Several groups working on loop quantum gravity and string theory demonstrated that their models naturally predicted a bound scenario where the universe contracted to a minimum size before expanding again. In such models, structure from the previous cosmic cycle could potentially survive the bounds, seeding rapid galaxy formation in the subsequent expansion phase. What's remarkable is the convergence, noted Dr. Tanaka in a follow-up paper. Independent approaches to quantum gravity, loop quantum cosmology, string gas cosmology, asymptotically safe gravity, all predict bound scenarios with similar characteristics, and all allow for pre-bang structure to influence post-bang evolution. This isn't just one speculative idea anymore. It's emerging as a robust prediction from multiple approaches to quantum gravity. Critics remain skeptical. Dr. Lawrence Perez at Princeton argued that bounce models faced insurmountable fine-tuning problems. To get the right amount of structure transferred to the bounds requires parameters adjusted to ridiculous precision, 1 part in a trillion or worse. That's not natural physics. That's cosmic conspiracy. We shouldn't abandon simpler explanations just because they require some adjustment to standard models. The debate raged through dozens of papers, conference sessions, and public lectures. Social media amplified the controversy, with physicists and astronomy enthusiasts debating the merits of different theories in real time. Science communication YouTubers produced elaborate videos explaining the competing frameworks to millions of viewers. The public engagement was unprecedented for a purely theoretical physics controversy. The breakthrough came in March 2026, when a team led by Dr. Emilia Zhao announced the detection of anomalous fluctuations in the cosmic microwave background at unprecedented angular scales. Using data from both Planck and the Atacama Cosmology Telescope, combined with new techniques for separating foreground contamination, they identified subtle patterns that had been hidden in the noise of previous analyses. The patterns were striking. Coherent fluctuations extending across enormous angular scales, 30 degrees or more across the sky, far larger than standard inflation models could produce. Even more remarkably, these superhorizon fluctuations showed correlations with the locations of massive galaxy clusters observed by JWST in the early universe. This is the smoking gun we've been looking for, Dr. Zhao announced at a press conference. These fluctuations are too large to have been generated during the standard inflationary epoch. They must have originated from physics operating before or during inflation, possibly from structures that existed in a pre-inflationary phase. And they provide exactly the enhanced gravitational seeds needed to explain rapid galaxy formation. The discovery sent shockwaves through the cosmology community. If confirmed, it would provide direct observational evidence for physics beyond the standard inflationary paradigm. Several groups immediately began independent analyses to verify the results. Within weeks, 3 separate teams had confirmed the existence of the anomalous fluctuations, though debates continued about their precise amplitude and statistical significance. Dr. Marcus Beaumont's modified gravity team rushed to publish calculations showing how their model could explain both the anomalous CMB fluctuations and the early galaxy observations simultaneously. Meanwhile, the bounce cosmology advocates demonstrated that their framework naturally predicted superhorizon correlations. Suddenly, theoretical speculation had become observationally grounded hypothesis testing. By mid-2026, a new consensus began emerging, not about the specific solution, but about the nature of the problem. The universe revealed by JWST and complementary observations was fundamentally different from the universe described by 20th century cosmology. The differences weren't minor technical details that could be patched over with small adjustments. They reflected deep gaps in humanity's understanding of cosmic origins and evolution. "We're living through a transition period," explained Dr. Rebecca Thornton during a Royal Society lecture. "The old paradigms serve us well for decades, but it's reached its limits. We're now in the messy intermediate phase where we know something is wrong, but haven't yet converged on the right alternative. This is simultaneously frustrating and exhilarating. Frustrating because we lack definitive answers, exhilarating because we're witnessing the birth of a new understanding." The James Webb Space Telescope continued observing, pushing deeper into cosmic time with each observation cycle. In April 2026, it detected galaxies at redshift Z equals 20, corresponding to just 180 million years after the Big Bang. Spectroscopy revealed they contained massive stars unlike anything seen in the modern universe, objects with hundreds of solar masses, burning through their nuclear fuel in mere millions of years. These behemoths, physicists realized, could have seeded rapid chemical enrichment and black hole formation, potentially explaining some of the mysteries. But even this discovery raised new questions. How did such massive stars form? What prevented them from fragmenting into smaller objects during gravitational collapse? The answers likely required understanding the detailed physics of primordial gas clouds in the early universe, physics that current simulations couldn't adequately capture. As observations continued through 2026 and into early 2027, the picture grew simultaneously clearer and more mysterious. JWST revealed that the early universe wasn't just surprisingly structured, it was surprisingly diverse. Some regions contained enormous galaxy clusters, while others remained relatively empty. The cosmic web of matter appeared to have formed far earlier than expected, with voids and filaments clearly established by Z equals 8, just 600 million years after the Big Bang. Dr. Wei's team at Caltech made a particularly puzzling discovery. Galaxies at Z equals 12 showed clear evidence of tidal interactions and mergers. The morphologies were disturbed, spectral lines were split by velocity differences, and in some cases, multiple nuclei were visible within. Single systems. This meant galaxies were colliding and merging when the universe was less than 400 million years old. Another process that should have required far more time to develop. Every observation makes the problem deeper, Dr. Wei admitted during a Journal Club discussion. "We keep finding evidence that the early universe wasn't just slightly more evolved than expected. It was fundamentally different. Galaxies were forming faster, merging faster, enriching with heavy elements faster. Either time itself moved differently in the early universe, or we're missing some massive piece of the puzzle." Some researchers began questioning even more fundamental assumptions. Dr. Elena Reeves authored a provocative paper suggesting that the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales, might not apply to the early cosmos. Perhaps the first few hundred million years after the Big Bang were characterized by extreme inhomogeneity, with some regions evolving much faster than others. Only later, through various smoothing processes, did the universe develop the uniformity we observe today. The proposal was controversial, but gained traction. Computer simulations incorporating varying initial conditions showed that extreme early inhomogeneity could potentially explain many of the JWST observations. But it raised a deeper question. Why would the early universe be so inhomogeneous? What caused some regions to evolve so much faster than others? As 2027 progressed, the astronomical community settled into a new normal. The crisis of 2025 had evolved into an ongoing investigation, with dozens of research groups pursuing different theoretical and observational approaches. JWST maintained its position at Lagrange Point 2, faithfully collecting photons that had traveled across cosmic time, each observation adding another piece to an increasingly complex puzzle. New instruments came online to complement JWST's observations. The Square Kilometre Array began operations in Australia and South Africa, providing unprecedented sensitivity to radio emission from the early universe. The Cherenkov Telescope Array commenced science observations, searching for gamma-ray signatures from processes in the distant cosmos. The next generation of gravitational wave detectors started taking data, hoping to detect signals from black hole mergers in the first billion years after Big Bang. Each new capability opened another window into the early universe, and each revealed additional surprises. The radio observations detected carbon monoxide emission from galaxies at Z equals 15, proving that molecular gas, the fuel for star formation, was abundant even at these early times. The gamma-ray telescopes found evidence of active galactic nuclei powered by supermassive black holes at Z equals 11, further confirming the rapid formation of these enigmatic objects. The gravitational wave detectors, though still limited in sensitivity, place constraints on the merger rate of massive black holes in the early universe. Dr. Sarah Kim coordinated an international effort to synthesize all available observations into a comprehensive picture of cosmic evolution. Her team included experts in galaxy formation, black hole physics, stellar astrophysics, and cosmology. They worked to identify which aspects of early universe evolution required revolutionary new physics versus which might be explained by better understanding of conventional processes. Their preliminary report, released in August 2027, acknowledged the depth of the problem while offering reasons for optimism. The observations clearly indicate that our understanding of the early universe was incomplete, the report stated. However, patterns are emerging from the data that suggest paths forward. The correlation between CMB anomalies and galaxy cluster locations points to enhanced initial density fluctuations. The prevalence of supermassive stars offers a mechanism for rapid heavy element enrichment. The efficiency of molecular gas cooling may have been higher in the metal-poor early universe. While no single explanation accounts for all observations, combinations of these effects might collectively explain the puzzle. What James Webb Space Telescope had truly exposed wasn't just the physical size of the universe. It was a conceptual size, the vast gulf between human understanding and cosmic reality. The observations had revealed that the universe contained depths of complexity that decades of theoretical work had failed to anticipate. Galaxies formed not in the leisurely, hierarchical fashion that simulations predicted, but through rapid, efficient processes that compress billions of years of evolution into mere hundreds of millions. The revelation humbled the astronomical community while energizing it. Young researchers saw opportunities for transformative discoveries. Established scientists reconsidered fundamental assumptions they'd held for careers. Theorists developed new mathematical frameworks to describe cosmic evolution. Observational astronomers planned ever more ambitious surveys to map the distant universe in unprecedented detail. As 2027 drew to a close, Dr. Elena Reeves reflected on the journey that began with that shocking observation in early 2025. We set out to study the first galaxies, and we discovered that our concept of first was naive. We sought to understand the early universe, and we learned that our understanding itself was in its infancy. In a sense, JWST's greatest achievement wasn't revealing how big the universe is. It was revealing how small our comprehension had been. The telescope continues its observations, peering into cosmic depths that challenge everything humanity thought it knew about existence itself. Each photon it collects carries information from a universe far stranger, far more magnificent, and far more mysterious than the pioneers of cosmology could have imagined. The journey to understand that universe has only just begun. The discoveries continue to accumulate, but definitive answers remain elusive. By early 2028, more than 5,000 scientific papers have been published analyzing JWST observations of the early universe. Conferences devoted entire sessions to debating competing interpretations. The field had entered a period of creative ferment, where established paradigms crumbled but no clear replacement had yet emerged. Several missions are now in development to address the mysteries JWST uncovered. The Origin Space Telescope, planned for launch in the mid-2030s, will study the infrared signatures of the first generation of stars. The Laser Interferometer Space Antenna, LISA, scheduled to begin operations in 2037, will detect gravitational waves from supermassive black hole mergers throughout cosmic history. Ground-based extremely large telescopes, with mirrors 30 to 40 meters in diameter, will provide spectroscopic details that even JWST cannot achieve. But the ultimate answers may require observations that current technology cannot provide. Some researchers argue that understanding the earliest moments of cosmic history demands direct detection of primordial gravitational waves, requiring space-based interferometers with baseline distances of millions of kilometers. Others suggest that solving the mystery requires a revolution in theoretical physics, perhaps emerging from a successful theory of quantum gravity. What remains clear is that James Webb Space Telescope has fundamentally altered humanity's perspective on the cosmos. The universe it revealed is not the universe anticipated by theorists or predicted by simulations. It is larger, not just in spatial extent, but in complexity, in diversity, and in its capacity to surprise and confound. The observations have demolished old certainties while opening new frontiers of investigation that will occupy astronomers for generations to come. Dr. Yuki Tanaka, whose theoretical work on pre-bang cosmology gained prominence during the crisis, offered a fitting reflection. Science advances through the interplay of theory and observation. Theory predicts what should exist. Observation reveals what actually exists. When the two diverge dramatically, as they have with JWST, it signals an opportunity for profound progress. We're living in one of those rare moments when the universe itself is teaching us that our imagination was too limited. The challenge now is to expand our thinking to match the grandeur of what actually exists. The story continues. The James Webb Space Telescope orbits silently at Lagrange Point 2, its mirror collecting ancient photons, its instruments recording data that humanity is only beginning to comprehend. Each observation pushes the boundaries of knowledge. Each discovery raises new questions. Each analysis reveals another layer of cosmic complexity. The universe has exposed its enormity, not through simple measurements of size, but through profound depth of mystery it contains. And somewhere in the darkness of space, light from even earlier times continues its journey toward Earth, carrying secrets from epochs we have yet to imagine, promising revelations that will dwarf even extraordinary discoveries of these past years. The universe, it seems, is always bigger than we think, and it's only just beginning to reveal its true scale.